Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and today we will be talking about algorithms. So, today is the first lecture in this series, and we start with the basic question: what is an algorithm? So, in this today's lecture we will see the definition of an algorithm, and then we will try to understand what an algorithm is by looking at an example, and then we will try to see how to analyze an algorithm. So, what is an algorithm? An algorithm is any specific set of step by step instruction for carrying out a procedure or solving a problem. For example, if somebody gives you a recipe for cooking some particular dish, say laddu, that is an algorithm for preparing a laddu. Or say in the high school you have done how to multiply two big integers, and there was some procedure of multiplying it, that is an algorithm. So, we have been used to algorithms throughout our life, although we have never analyzed an algorithm or mathematically studied one, but algorithm is nothing new to us. In this lecture we will see how to look at algorithms in a more mathematical and scientific way. Hopefully in the next few lectures we will go into more and more detailed and more non-trivial algorithms. So, an algorithm is expected to have one basic property, and that is an algorithm is expected to terminate at some point. So, it should not be that an algorithm keeps on running forever and ever and never terminates. So, termination is a very important aspect of an algorithm. So, let us start with an example that most probably all of us have seen in our primary school or high school, and it is that given two integers p and q, we want to compute the greatest common divisor, or in short GCD of p and q. Now, what is a GCD? GCD is also known as highest common factor or HCF. So, GCD of two numbers, two integers p and q is the largest number that divides both p and q. Now, GCD is only defined for positive integers. So, integers of the form 1, 2, 3, 4, 100, 1000 and so on. It is not defined for negative integers or for non integers like half or 1/3 or something. So, given two numbers p and q, now if they are integer, positive integer, then the largest number that divides it, the largest, is called the GCD of p and q. We will see some examples. Say for example, if p is 14 and q is 8, then what is the GCD of it? So, it is the largest number that divides both 14 and 8, and 2 is the number. Note that nothing more than 2 can divide 14 and 8 simultaneously. Similarly, for p is 12 and q is 18, it is 6. Of course, 1 divides both of them, 2 also divides both 12 and 18, 3 also divides both 12 and 18, and 6 also divides both 12 and 18. Note that no other number divides 12 and 18 simultaneously. Among the set of numbers that divide both 12 and 18, 6 is the largest number, and hence GCD of 12 and 18 is 6. So, now we have understood what the definition of GCD is by using some examples. Before we start to look at an algorithm of computing the GCD of two numbers, let us see some properties of GCD. The first one is very obvious, that GCD of P and Q is equals to GCD of Q and P. So, it does not matter which one is told first. If 2 divides 8 and 12, then 2 also divides 12 and 8. Second one is that if one of the numbers, say the first number, divides the second number, so P divides Q, then the GCD of P and Q is P itself, because nothing more than P can divide P itself, and P divides both P and Q. The third and the most interesting of them is if T divides, T is some other integer that divides both P and Q, then T also divides the GCD of P and Q. Okay. For example, in the case of 12 and 18, the example of when P was 12 and Q was 18, we saw that 1, 2, 3 and 6, all of them divides P and Q. GCD was 6, but note that 2 also divides 6 and 3 also divides 6. It is not coincidence. So, now that we have understood what a GCD is, GCD of two numbers is, let us try to compute the GCD of two numbers P and Q. Now, as we are doing the examples, we have already seen some algorithms which was running in our head. Let us formally see what is going on. So, this is almost what can be called as an exhaustive search, right. So, for example, when we are computing GCD of 12 and 18, what were we doing? We first in some sense in our brain wrote down all the possible numbers up to 12, because we all know that nothing more than 12 can divide 12. So, all the possible answers that can be for GCD of 12 and 18 is 1 to 12. And then what did we do? We went one by one and say, for example, we saw 1. 1 is a number that does divide 12 and 18, and so we mark the 1 as a possible answer to GCD and we mark it as red. Similarly, 2 is a number that divides both 12 and 18 and we mark it as red. 3 again is something that divides both 12 and 18 and mark it as red. But 4 is something that does not divide 18, although it does divide 12, but since it does not divide both of them, so it is not a possible answer, so we do not mark it as red. Similarly, for 5, and we come to 6 and we see that 6 does divide 12 and 18 both, and thus 6 is a possible answer, 6 is marked red. And note that none of the other numbers we can easily see ourselves that they do not divide 12 and 18, and hence they are not marked as red. So, after this whole thing is done, in our head we have this calculation that 1, 2, 3 and 6 are the possible answers that can be for GCD of 12 and 18. And now what is the GCD? We move from right to left, and as soon as we see something marked red, that is of course the largest number that divides both 12 and 18, and hence which is in this case this number 6, this does divide 12 and 18 and is the answer to the GCD. So, now that we have done the high level understanding of what the algorithm should be, at least by an example, let us try to formulate or write down an algorithm of formal algorithm to find out the GCD of two integers P and Q. So, what I have written here is what is known as a pseudocode. A pseudocode is not a program or a exact code that you can fit in a computer and get the answer to it. It is not a computer program, it is not a C program or a C++ program or a Java program. As you can see, for people who are used to this kind of programming languages, there is not any semicolons or any other such kind of things that are used in C or C++ or Java or any language for that matter. So, this is just a step by step instruction of how to find the GCD of P and Q. It's a very common term to be used. It's called a pseudo code because it's almost like a code, but not a code. And now let's look at this algorithm. So we call this algorithm the basic underscore GCD PQ. And what do? We first look at have an array A which has p elements, and we initialize all the elements to be black. This is exactly same as like we wrote down 1 to 12 and colored all of them black, right. Now in the next step what we do is that we go from 1 to p, slowly increasing, and as soon as we find some I that divides both p and q, we mark the ith index of the array A as red. This is exactly same as we have done for this example. And now after we have done all of this marking of this all the array elements, array indices, we start from right to left, which thus we go from p to 1, and as soon as we find the first red, remember the first red is the largest integer that divides both p and q. So we output that index, the index is the GCD, and we exit, that is the stop of the algorithm. Now this algorithm looks simple, it is intuitive, and it is seems logically correct, but we are not usually happy with just that kind of stuff. We need to prove that the algorithm has some other properties, and in fact mathematically prove that the algorithm is correct. An algorithm when written in the pseudo code requires to have we need to prove 3 properties, which we call it as correctness, and we somehow have to understand the quality of the algorithm. So the first thing is to prove that the algorithm does terminate. It is something that we done in the first slide only, and that is an essential condition of an algorithm. The second algorithm essential part is that the algorithm should be outputting the correct value, which is the in this case GCD of the two numbers p and q. And the last part is we have to check how good is this algorithm. So this is the part when I will explain more later on in this lecture, but for now let us look at the first 2 bullet points. So to start with, let us try to prove the termination of this algorithm. So you have to prove that the algorithm under any kind of integer, positive integer p and q should terminate. Okay. There is no guarantee that if p and q are not positive integers, the algorithm will terminate. That is not something we would promise at all, but if they are both integers, positive integers, they should terminate is what we want to ensure. In the first loop, which is this part, the I goes from 1 to p, which means that I goes from 1 to p. So it runs for p steps. So there are p different steps that is measured, and so the first loop would stop after p steps. The second one, which is the second loop, which is this part, note that it is also a for loop from 1 to p. So it also is a p steps, or the for loop will run for p times, except that every possible loop we will be doing couple of operations. We will first check if I divides p and q, and then we will end up writing down, marking this ith index as red. Okay. So this second for loop will run for 2 p steps, although it will run for p steps, but in each step it will take, each for loop step it will take 2 operations. So 2 p steps. So after 2 p steps, the second for loop ends, and the third for loop, which is basically the remainder of this, all of them, it is not that you would go from p to 1, and since it go from p to 1, and as soon as we find a red index, we will output it and stop. So as such, it might happen that we will stop as much before we have gone to j goes to 1, but in the worst case we might run for p steps, and more importantly after p steps this loop will also stop for certain, and thus this algorithm will stop after 4 p steps. So, this is a proof that this algorithm will terminate. The next thing to prove is that the algorithm outputs the correct value, and then we will go on to understanding how good the algorithm is. So, let us take a small break now, we will come back and continue on this. Welcome back after the break. So, before the break we looked at the algorithm for computing the GCD of two integers, positive integers p and q, and we did look at the proof that this algorithm does terminate. The next step is to prove that the algorithm does output the correct value. So, this is what we call this correctness of the output. So, first of all, as we can say that if the GCD is p of p and q is k, then k should be less than or equal to p, because anything more than p will not divide p. So, the fact that we are looking at just the arrays up to p is fine. Since k is this GCD of p and q, since k divides both p and q, so at some point in the second for loop, when I will be equal to k, k would be marked as red. So, what we have now is that the GCD value, the actual GCD value will at some point surely be marked red. The third thing is that for no elements greater than I will divide both p and q, that is by the definition of GCD value, which is k. I mean nothing more than k can divide p and q, else the GCD would have been that bigger object, bigger number. So, no other I greater than k would be marked red, and thus in the third for loop, when we start from the largest j equals to the largest to the first, we will always output the right value k. So, that is the correctness of this algorithm. It was kind of easy to see that the algorithm was terminates and correct. I have done this one rigorously in this for this particular algorithm, mainly because later on we will encounter much more complicated algorithms, where even proving the termination and the correctness of algorithms is very hard or non trivial at least. So, now comes the more interesting part is what do we mean by a good algorithm? It is something that is not very obvious, but in general the goodness of the algorithm is measured by the amount of resource the algorithm is taking. The resource that most of the time we are interested in is time, something that all of us know that time is precious, and in particular when we run a program on the computer we expect it quickly give the output, give the answer. So, time, or in our case is the number of steps that the program or pseudo code will take, is something very crucial. The other thing that is used is what is known as the amount of space, or you can think of it as the amount of hard disk space that will be used or something, or in other words it is the amount of registers that will be kept and so on. We will see more of it. Note that this is not necessarily the only set of resources that one studies. There are other set of resources, for example, the amount of electricity consumed, or the amount of times the algorithm will have to look up at some table, etc. There are lots of resources that we usually look at to analyze how good the algorithm is, but in this talk we will only be focusing on these two things, time and space, and in general this is how we will be going about in most of the lectures in this series. First of all, how do we calculate the number of steps? The most commonly used analysis for the number of steps is what is known as the worst case runtime, or it is the number of steps that the program will use in the worst possible input. So, it is under any given input, the algorithm will surely stop after this much steps. This will be called the worst case runtime. A similar one can be told about the average case runtime, which is on average this program will stop after this many steps. So, that will be the average case runtime, and we will encounter both of these concepts later on in our lectures. So, clearly the average case is less than the worst case, and there are lots of discussions about which is the right concept to be used for understanding the algorithm, and we will be looking at both of these things. Let us consider our algorithm, this basic GCD that we have done, and let us look at the runtime. So, in the first case, in the first for loop, this is exactly how we did this termination process also. The first for loop runs for p steps. I will not go over this argument again because we have already done it. The second for loop again takes 2 p steps, that also we have seen earlier in the termination case, and the third for loop will take less than or equal to p steps, or just in the worst case runtime situation it would surely take p steps, right, and the worst case runtime is 4 p steps. The average case might be something slightly lower, but in the at least in the worst case it is 4 p. So, in general when we talk about an algorithm, so an algorithm is something that is given an input x, it is takes as input and it outputs, gives the output. Now, the running time of the algorithm is always measured as a function of the input size. Now, this is something that is very crucial to understand what is an input size. An input size vaguely is the amount of bits required to explain the input. We will see more of it very soon. Say for example, in our algorithm of the basic GCD, what is the input? The inputs are 2 positive integers p and q. Okay. Now, p will be given as binary because we are talking mostly of computers, but if we are talking of normal digits it will be given in the decimal, but let us look at the computer setting in which the p is given in binary, and thus it will take log p to the base 2 bits to write it down, right. Similarly, q is another input and it will also take log q to the base 2 bits. So, the total input size is n plus m, where n is the bit length of the first integer and m is the bit length of the second integer. Okay. And what is the running time? We have already done that. The run time is 4 p. We saw it in the 2 slides earlier, and now 4 p is 4 times 2 to the power log p to the base 2. This dot is indicating a product. And now, what is log p to the base 2? This we have know is equal to n. So, this is 4 times 2 to the power n. So, the run time is actually 4 times 2 to the power the input size. This is what we call as exponential. This is what we call as an exponential runtime, meaning since this n is, which is the bit length of the input, and the runtime is 2 to the power n. So, this algorithm basic GCD has runtime exponential in the input size. Now, let us come down to this next concept, which is the space. And again, note that what are the space required? When we are doing this algorithm, we had to maintain or preserve the whole array, which was this all the p values that came, all these p values that was there. So, we had to store this whole array with p values, and that meant we need p bits of storage. Now, again what is p? Recall that p is equals to 2 to the power n, where n was the input size. So, space complexity is also exponential in the input. When we look at this algorithm basic underscore GCD, this algorithm computes the GCD of two numbers correctly. That the first thing that it does terminate and produces the GCD of these two numbers. Second thing is the time complexity is exponential in the size of the first input, and the space complexity is also exponential in the size of the first input. Okay. So, this is what we say as the analysis of this algorithm that we have. Now, question is this algorithm good enough for us? And to understand it, we have to understand what we expect from an algorithm. So, in general, when we are designing an algorithm, we have some goals in mind, namely we have to solve the problem correctly, to minimize the runtime as much as we can, and 3, minimize the space complexity. We will see more of it, and we live with this question that can we do better than the algorithm that we described for computing the GCD of two positive integers, and we will answer this question in the next lecture. So, to summarize, we gave the definition of an algorithm, we saw an example which is the computing the GCD of two integers. We saw how to analyze an algorithm, we looked at its runtime and the space complexity. By the way, I might have forgotten to tell you that runtime is also known as the time complexity. So, it is the time complexity and the space complexity that we look at, and I leave you guys with a question. Try to change the algorithm a little bit, so that at least you can reduce the space complexity to 1. By 1 I mean here any constant will do. I leave you guys with this problem or question to think about, to ponder, and we will come back next lecture to see more interesting algorithms for computing the GCD of two numbers. Thank you.